Hello, and thanks for coming back. This is episode 2, and we're going to be talking about mass, length, and tension, and how it relates to sympathetic resonance. To get right into it, these 3 things are huge contributing factors because it depends on the pitch. Hi, welcome back to episode 2. We're going to be talking length, mass, and tension and how it contributes to sympathetic resonance. So every object or physical thing has a frequency that resonates with it, as we talked about before. I just wanted to go more in depth with that, with how these things heavily contribute to that. Length. The length of an object defines how much air or gas is displaced at the speed of sound. So, like a flute, this is a small flute. The length of it is pretty small in comparison to like a bassoon or a tuba. But I just learned this from Walter Lewin in his physics classes. But the holes are here to shorten or lengthen the amount of air that is being displaced or gas that's being displaced within the instrument in the body that it has. Since it's a small body, it's going to be relatively high because there's not that much gas or air to dissipate. So, like this. So as I shorten the amount of length from where the pressure is coming from to where it is released, as I went closer, it got higher. So that seems relatively simple. Talked about the mass of it. If this was a tuba, obviously it would be way, way deeper because there's a lot more air to move around in there. Tension. Tension also is a contributing factor because how hard the force is going. So that's one note, and I can do, with holding the same length, I can do it higher because I'm pushing air faster, allowing it to oscillate faster at the same note. So that first note looked more like this because I'm putting an amount of air in, but I was able to get the octave with the same length and the same mass because of the tension of how hard I was pushing air in. You can also think of it, I think I said it in the first video, with a violin. Same idea. You put a string open, you play an open E, it plays, and then as you put your finger down on the bridge, and as you go up and up, the string gets more tense because you're pushing down on it closer to one end, and it gets obviously higher. So all these contributing factors, and like it depends on the temperature of how fast sound is going to travel in whatever space you are, which is why like instruments get out of tune, whether it's like too hot and all that stuff. So all of these are acting simultaneously at the same time to contribute to sympathetic resonance. A really cool equation that I found to be able to calculate this is this. Fn equals NV divided by 2L, in which Fn is a certain fundamental that you're trying to find, N is the fundamental you're trying to find. V is the speed of sound. This doesn't contribute to temperature or what gas you're doing, I don't think. Divided by twice the length of the instrument, or whatever object, mass object. So I looked up that a tuba, in some cases, let's just say for now, that a tuba is 5.4 meters long. So this is the fundamental. This is the length. L equals length. Sorry, I'm going way all over the place. But okay, 5.4 meters times 2, twice the length, equals 10.8. So you got 10.8. We're trying to find the first fundamental, so F1 equals 1 of the speed of sound, which is 340 meters per second. So 1 times 340 divided by 10.8. And it comes out to the fundamental, let's erase this. The first fundamental of the tuba is like how low it can go, equals 31 hertz. Around. I mean, there's like a lot of other contributing factors, but that's a really good way. You can do it if you want to find the second fundamental, third, all that stuff. This is also, I'm not going in depth with timbre of the instrument, because obviously a tuba at 31 hertz versus an organ pipe at 31 hertz is going to sound a lot different, because one is brass and one is two pipes. Yeah. I'm also not coming into account amplitude, which we'll cover in the next episode. But in a very scattered way, this is how length, mass, and tension contribute to resonance. If that made any sense. Who knows? Doesn't matter. But thanks for watching. Next episode, we're actually going to experiment on real instruments, which I'm very excited for.